This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Developers, are you ready? It's time to upgrade your data platform to InterSystems Iris. Choose your language, choose your tools, choose your environment. Collaborate, build faster, and deploy more efficiently. When you can make faster decisions, there's no telling what you'll create. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris.
Welcome to Software Engineering Radio. I'm your host Gavin Henry, and today my guest is Bert Hubert.
Hello.
Hi Bert. Bert has had a 20-year track record in commercial and open source software development. He is the author of the open source PowerDNS nameserver, which powers around 50% of all internet domain names in Europe. Bert is active in the IETF and works on the standardization of DNS. Bert, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
No, this was good.
Excellent. During the show, we'll be talking about DNS security in general, with the second half of the show talking about DNS over HTTPS, or more commonly known as DOH. However, I'd like to start with an overview of DNS. So, what is DNS in its basic form?
We used to be able to say that, look, DNS is like the phone book of the internet. It's no longer working because younger people have never seen a phone book. So it's become easier to say that the phone book is like sort of DNS of telephony. Whenever you type in a name on the internet, computers cannot directly connect to names. They connect to IP addresses, IPv4, IPv6. And DNS sits between you and the IP addresses. So whenever you want to connect to a website, your computer needs to look up what is the IP address of that website, and DNS provides that. And in addition to that, it's not just IP addresses for website visits. DNS also tells you where the mail server for a domain is located, for example. So without DNS, we like to summarize it over at PowerDNS that without DNS there is no internet, and if your DNS is slow, then your internet is slow. And if your DNS is sort of working so-so, then your whole internet experience will be so-so.
Okay, so what is the current protocol? What does it look like?
Oh, that's a good question. So it is an old protocol. So the first roots of DNS go back to like 1983 or something like that. And it was influenced by Pascal, which is a programming language was sort of popular in academia at the time. And it is a binary protocol. So whenever you look something up, packet has to be crafted. And this packet contains the query, of course. But it's not anything you would recognize as JSON or as XML or whatever. It was written in a time when every bit counted. And they tried to make sure that almost every DNS message and almost every DNS response fit within 512 bytes. Because that was the maximum packet size that they thought they could reasonably use. And because of that, there is actually, the protocol is like fully binary. And domain names are, for example, compressed internally. So if you have a DNS query that has a bunch of answers, then instead of repeating the names of all those answers, it will contain pointers back to the original previous answer. So it is a binary protocol with built-in compression. And you can imagine how well that went, because the amount of DNS exploits and crashing bugs we have seen since 1983 has been like stunning. So in short, it is a very old protocol that we rely on all day long, and it's tricky to get right.
So I wouldn't class that as simple in today's terms?
No. It's definitely not simple. And you see, for example, that often it's messed up. So for example, DNS knows the difference between this name does not exist. So let's say I want to go to PowerDNS.uk, and that name probably does not exist. And so that's one kind of DNS error. But there's a second DNS error that says, well, the name exists, but it does not have an IPv6 address. So that's a nuance beyond that name exists or it doesn't exist. It says the name exists, or the name does exist, but the thing you asked for does not exist. And many implementations will mess up these two different outcomes. And for example, many load balancers, even to this day, when they do DNS, if you ask them for the IPv6 address of a website, they will very frequently give the wrong answer. So they will answer the whole name you asked for does not exist. They will not say the IPv6 address does not exist. They will say no, the whole name doesn't exist. And this has in the past led to like really big brand name websites disappearing from the web because a big load balancer messed up this kind of nuance.
And they all do the DNS themselves, I take it?
Yeah, so for a very long time, people used to use the very good bind name server for everything, to the point that when we started PowerDNS, the only way we could describe ourselves was as a non-bind name server. So bind is this was not the first name server, not by a long shot even, but like in the 1990s, it was the only name server around, to the point that, we had to describe ourselves as a non-bind name server. Recently, people have started to craft their own name server things for all kinds of products, and they've been doing a terrible job at it. It is a protocol that is fiendishly difficult to get right. So it's not simple, and there is a lot of dubious code out there.
And do you mean when we called ourselves, do you mean the Power DNS Project?
Yes, so we got launched somewhere in 1999 because someone wanted to do geographical load balancing via DNS, so that American users would end up on American servers and European users would end up on European servers. And back in the late 1990s, this was a very, very novel idea where people said, it cannot be done, it's impossible, and we did decide to do it. And when we tried to market our product that we built a name server, people said, so you sell bind. And we said, no, we made our own name server. But that was such a strange concept at the time that we in our marketing we just had to sell ourselves as a non-bind name server.
I see. Talking about load balancers and CDNs, on show 347 we interviewed Daniel Corbett on HA Proxy, which I think discusses DNS there. And we also did show 345 with Tyler McMullen on CDN networks there for the listeners to review again. So if we take the usual scenario, not server side but browser side, you or I go to our browser of choice. There's a handful of choices nowadays. You type in the website and then it does the DNS lookup. What you've explained already is IPv4 and IPv6. So that would be an A record and a AA record, is that?
Yeah, we actually call it a quad A record.
Quad A, okay.
And because it's easier to pronounce. So it's actually the action starts earlier than you say, even as you are typing a URL in the URL bar, now that we still have it. But while you are typing it, DNS lookups are already being made. So we very often see these partial requests happening. And then when you finally hit enter, then it's likely that the DNS lookup has already completed in the background. And indeed, it does simultaneous IPv4 and IPv6 lookups. And it will also then attempt to simultaneously set up connections to the IPv4 and IPv6 address and start working on which chain finishes first. So if the IPv6 lookup and connection finished first, that's the server that will actually get the request. And this is the so-called happy eyeballs principle. And it turns out that this already is complex enough to get right, because especially IPv6, and we love IPv6 very much so, more than our users, I would say. But IPv6 queries far more often than you'd like come back with errors, for example. So the correct answer is, of course, here is the IPv6 address for the website. The second best answer is, well, the name exists, but it doesn't have an IPv6 address. But quite often you get back the answer, the whole name doesn't exist, or you get an actual error back that says, we tried to resolve this name, but we got timeouts, it didn't work. So quite a lot happens behind the scenes to make DNS work really well. And that's important because, like I said, if DNS is a bit slow, the whole browser feels slow. So browsers by now, they do a lot of tricks to make sure that their queries get answers pronto, because it really impacts the user experience.
Yeah, it sounds like there's more than a handful of DNS requests going on as soon as you even think about going online with a browser.
Yeah, if you look at DNS traffic that is coming out of a typical household right now, and because of the functions we fulfill at some of our deployments, we have statistics on how much DNS is coming out of a household. And that is, a typical household now generates, I think, 1 DNS query per second or something like that.
Oh, wow.
And that's a whole household, by the way.
And apart from the A and Quad A records, what else do you typically see being stored in DNS?
Yeah, so as mentioned before, when you do send out email, the right mail exchanger needs to be found. So that's a so-called MX record. And you see a lot of those, both on the sending side. So one of the things that, for example, that you can do with DNS is if you have a network with millions of subscribers on there, and you're worrying about bad behavior going on there, like servers that have been hacked. And one of the surest ways of finding if a server is hacked is checking how many MX domain queries it is doing. Because many servers that have been hacked will furiously attempt to spam the whole world. So then you see tons of MX records going by. And a close second, or they might even be more important than, or at least more frequent than MX records, are so-called text records. And text records were just meant to store arbitrary bits of text in DNS for whatever reason. And if you look what has happened, these text records are now used by many spam lists where you can look up if this IP address is known to be spamming, or if this domain name is known to be involved in phishing. So many mail servers will perform a DNS text record lookups to figure out if a sending mail server is actually known to be spammy or not. And it's interesting that DNS was used for that technology, because to this day, DNS, with all its faults and all its age and all its cruft that has grown on it, it is the one single technology that you can, with very limited investment, say, hey, I can make a worldwide distributed database, and you can ask it tens of thousands of questions per second and you will get good answers. And that's the kind of thing you need. For example, when you need to do a dozen lookups for every email message you see. So summarizing, it's MX records and text records mostly.
Yeah, I think it's a product of its time, where similar to the routing protocol BGP, where they're both really good designs, and they were designed with a limited bandwidth and limited space, so it really did force your creativity.
Yeah, I would have to agree. The limitations at the time were stark. There were many things that we would do differently right now. And also the expectations were different. So DNS, for example, relies on the internet being a nice place. So when you ask a DNS question, this does not happen usually over a TCP IP connection. It happens over a UDP connection. And a UDP query is just throwing out a packet to a server. So it does not set up a connection, it just sends a single packet. That's extremely efficient. And then when the response comes back, that response is contained in another packet. And of course, as a client, you would like to verify that the packet that came back in response is actually the right answer, that it was not a packet that was sent by anyone else. You want to have a big ID on there to make sure that the response matches the query. And these days we insist on like 64 bits of security for that kind of thing, so that people don't randomly send answers that might get accepted. And it turns out that in DNS, on every query and every response is a 16-bit, a 2-byte field, and that's the field that tells you that this answer is the right one. And that was fine at the time, because they said, yeah, that means that you need to send thousands of packets if you want to spoof in a fake answer. And then no one is going to send thousands of packets, because that they couldn't imagine that happened. And these days we can send 1,000 packets in a millisecond. So it turned out that protection level, that 16-bit protection level that they put on there in 1983 is completely inadequate by today's standards.
It's like the adage, who needs more than, 2K or 2 meg?
Yeah, 2K, yeah. And actually, when you go back, when you ask people, say, why did you use only 16 bits of security? And the answer was sort of stunning. They said, we didn't even mean it as security. It was just a sort of to make it more CPU efficient to match the question to the answer. They didn't mean it as security. And to make things worse, in the original specification, they also said, because of the way computers work, if you send a question to nameserver with IP address A, you might get back an answer from IP address B, which we know as spoofing. We now see this as a man-in-the-middle attack. And the RFC at the time helpfully, so the RFC is an internet standard, and the RFC helpfully said, if you get an answer back from the wrong IP address, you should still accept it. And we cannot imagine that anymore. But on the other hand, we have to realize that we use the protocol. We were, at least I wasn't around designing internet standards in 1983. And it was a different world at the time.
What types of DNS servers do we have?
Yeah, so it's important to realize that there are multiple kinds of name servers. So you have a so-called authoritative name servers, and these are the ones that say, I know all about PowerDNS.com, and this is the IP address of www.powerdns.com. So these are authoritative servers that know what they are talking about. But it's not enough to have an authoritative server, because anyone could start a server that says, I know everything about PowerDNS.com, but no one would be able to find that server. So to solve this sort of chicken and egg problem, everything on the internet starts with the root servers. And these are now, I think, over 1,000 servers with 26 IP addresses. And you can always ask a question of these 26 IP addresses, and you will get an answer. It might not be the answer you want, but it is an answer. And this root server is authoritative for the whole internet. So that's good. I mean, that sounds nice. I'm authoritative for the whole internet. Root servers effectively don't know a lot, but they do know that if you ask a question for PowerDNS.com, they know that, actually we don't know the answer to that, but we know that the .com servers, they know the answer, and you should ask them. And then the root server helpfully gives you a list of IP addresses for the .com servers. And the .com servers, we can ask them. We can say, hey, dear .com server, what's the IP address for PowerDNS.com? And the .com server will again say, I don't really know, but I do know where the PowerDNS.com name servers are, and maybe you should ask over there, and here are their IP addresses. And then finally you end up with this authoritative server that I started this story with, and that one can actually tell you, this is the right IP address. Okay.
So 26 IP addresses sounds a bit familiar to something else that has 26 things in it.
Yeah, and it is still a lucky accident.
Okay.
But I'll get to that, because it ties into the 512 byte packet limit I mentioned originally. But now to find our way among all these authoritative servers, that was originally thought to be too much work for simple computers. So a separate server was invented for that, called a resolver or a cache. And this resolver or cache, that would then traverse all these authoritative servers, starting from the root server, to find the answer to your actual question. And that is actually still the model that we have. So in your browser, you type the domain name you want to visit. The browser sends the query to its configured resolver that is part of your local network typically, and that one will troll the whole internet for you and consult different authoritative servers until it finds the right answer.
So the resolvers come with a predefined list of things?
Yes, this is the so-called hints file, and the hints file contain a suggestion, a list of around 26 IP addresses, and that list might be outdated. It might be that you turn on your computer and it hasn't been turned on for a few years. So at startup, a resolving name server will try all these so-called hint records to see if it can find a name server that answers. And typically we see that out of the sort of 13 IPv4 and 13 IPv6 records, we see that one or two of them change every year. So even if you had not turned on your resolving name server since the past 15 years, it would have found one IP address that worked, and from there it would have learned the latest list of 26 IP addresses.
That's pretty impressive that it has that longevity.
Yeah, I think that came from a time when people realized that a computer that you haven't done any administration on for the past 10 years is bound to be hacked by now and be operated by a troop of Russian hackers that you don't know. At the time, they thought it was very important that machines that had not seen any maintenance for the past 10 years would still work well.
And these 26 things, I read somewhere about K and A and B.
Yeah, so they affectionately are known as A root or B root or whatever, C root. And they run from A root to M root. And each of them has a history where it came from. So A root was sort of the original root server of the internet. And today it is being operated by VeriSign. That used to be Network Solutions. That goes back into the dark ages of the internet. And for example, F root is operated by the Internet Software Consortium, the people that also make the bind name server. And then K root is run by RIPE, the European IP address people. So each of them has a host and where it lives. So NASA has one, and the Japanese IPv6 project has one, and that not that long ago, these were actually these 13 servers were also actually physically like 13 servers that you could visit. So I visited a number of them, and it is sort of fun to sort of stand next to one of the roots of the internet. But these days, through the miracles of Anycast, it has now become possible to take a single IP address and have it be served by hundreds of computers all over the world. And so I haven't run the latest numbers, but I would guess that if you physically look at how many computers are doing root serving right now, that is a number that used to be like 13 and is now probably closer to 1,000 or maybe even 2,000.
Yeah, it really does show you how critical DNS is to the internet, that it's safeguarded by all these independent companies.
Yeah.
I'd like to move us on a bit because we're running out of time a little bit. So when we use the recursors, they have a list of hints in their database, and then they go and validate that and speak to the root. If we talk about trust, how does PowerDNS.com get into the whole system? You know, how do you, if you forget the commercial side of buying it, but how does that get registered within the core of the DNS, and how does that get trusted? Just a semi-brief answer so we can move on to another question.
Sure. So actually there is a whole parallel network. So we have the name server, the DNS protocol by which we ask questions. But if I want to get my name registered in the .com zone, I will have to convince a registrar, which is a company in between, that I own that domain and that they should publish my changes. And so this is actually, we have a downstream protocol that's DNS. So once the data is out there, you can ask queries using DNS. But if you want to change DNS data, there's a whole zoo of protocols, some of which are standardized, called EPP, for example, and many of them that are not standardized. So actually the whole authentication business of how do I make changes to publish domain names is far messier than how do you actually send out queries.
And how does the registrar prove who it is to get the domain name registered, as it were?
Oh, that's a really good one. And to be honest, I don't really know. It's sort of interesting that I don't know, because that shows you how big the separation, the gap is between the people that serve DNS names, which would be my business, and how people register domain names. And I assume there are blobs of XML which are being signed with certificates, but to be honest, I don't know.
I looked at it I've got a business in the UK to get registered with Nominet, and it's quite a process. It's like creating a new business, really. You've got to prove that you've got a customer base, that you're trustworthy, that you can do all these things. And I'm not surprised it's something that you don't really know about unless you've tried to sell domain names.
Yeah, no, but it's good that it's somewhat difficult, because the people that are operating in there, they have the power to register domain names and change them on your behalf. Because you make no mistake, if you register your domain name somewhere, you can do all the security that you want, but the place where you registered the domain has full control over your domain name, and they could change everything about it. It is crucial that you register your domain at the right place.
Exactly. So as software engineers, why is DNS so important to us when we're writing internet-facing software?
It always sits between you and the client, or if you are the client, it sits between you and the server. And unless you're really fond of typing in IP addresses, then there is no alternative. You always have to pipe your stuff through DNS if you want it or not. And the interesting thing is that actually being in the DNS world, we are rather fond of using IP addresses because they always work. So I recently launched a project that has to connect to servers, and for the longest time I did not actually support DNS lookups in there. I told people to connect to fixed IP addresses. And when that no longer scaled, I started using DNS, of course. But there's sort of an irony in there that I come from this. My whole company is called DNS, and we're like, well, let's see how far we can get without DNS. But in general, you will always, everything you do touches DNS. And if you want it or not. So for example, if you look at the DNS queries that come out of a typical enterprise, you will see all kinds of failed projects in there, old servers, companies that have been acquired and stuff. Everything is DNS. So even if you want it, and I'm not saying it's great technology, it's just that it's very difficult to not use it.
And do you recommend that anyone ever runs their own resolvers as a software engineer or authoritative DNS, or do you suballocate that to a different team?
No, in a typical enterprise situation, you had best say, look, there's no competitive advantage for you to run your own resolver. That's really something that your network provider provides, and it will not get better if you run your own from an enterprise setting. The answer is very different if you are at home and you don't trust your internet service provider. But if you are in a professional setting where you don't trust your network, you're probably in the wrong place.
Yeah, I see. That might be something we'll touch on a bit when we get to the DNS over HTTPS. Okay, so I'd like to shift us along a bit. So now we've covered what DNS is. Obviously, we could speak hours about more detail of what DNS is, but I think that's a good foundation.
Yeah, we could, yeah.
I'd like to discuss as many of the bad things that we have time for that can be done to it. So you can tell us a little bit about DNS hijacking.
Yeah, so DNS is vulnerable in a number of ways for being hijacked, but the story is actually slightly different than you might think. It is possible to fake DNS answers because the original DNS protocol has no encryption on it, no authentication, there's no integrity. So if you sit on the wire and you have the ability to change packets, you can just invent your own DNS answers and no one will know. This was typically seen as very bad, and of course it is very bad. But in reality, turned out that it's pretty difficult, because if you are the man in the middle, you can already do a lot of things. And the main worry was really not so much the man in the middle, but was the man on the side. And by that I mean that, let's say, I know that someone's house, they're watching a lot of YouTube videos or whatever, and so I flood their house with answers to the question, what is the IP address of youtube.com? I just keep sending packets that contain the answer to the question of the IP address for youtube.com is 1.2.3.4. And then the idea was that eventually one day my fake answer would be accepted and your computer would connect to 1.2.3.4 and not the real YouTube server. And in practice, it turned out that this, on a modern internet, this is extremely difficult to do and has not been done a lot in practice. What has been done a lot in practice and has been extremely painful is where DNS gets hijacked administratively, by which I mean we don't hack the protocol, we just move your whole domain name to new servers. And why has that been so successful? It turns out that there has not been a tremendously good focus on the registrar security bit. So you may have a very good secured network, but in the end your domain name is controlled by a very weak password. And this has been exacerbated that the original and often most important domain name for a company has been registered by the founder originally in the early days of the company when there was no security department. So the password might be as strong as password 123. And this has caused a ton of pain where people's domain names have been moved away from them administratively, and then they had to have a fight to get them moved back to themselves. So I would say that DNS has been attacked more administratively than technically, oddly enough.
What would you call that type of attack?
I think they do call it, they call it, for example, a registrar hijack.
Okay.
And there, I think in the US, the NCSC created a special name for it. which I don't know right now. But the key insight here is that if you run your own business or if you are in charge of domain names, try to figure out for all your important domain names who actually controls those domain names. And you should pay very special attention to the account recovery capabilities, because more often than not, the original founder registered the domain name from his Hotmail account, which is still around and may be long compromised. And then an attacker can go to the registrar and say, hey, I lost my password.
So that falls into the normal type of social engineering.
Yes. So these are normal attacks. Yes, it is, but it turns out that people pay a lot of attention to all kinds of things, and then the most important password of all of them, which is the password that controls the whole domain name of the company, is single factor and super weak. And I would classify this as the biggest risk to DNS right now.
Yeah, I mean, why would you go into flooding a connection with UDP packets that aren't ordered, as much as you can, when you can just call up technical support and say, I forgot my password.
Yeah, I forgot. Yeah. Well, actually, if you look at most big banks and if you look at Google, for example, most of the really big privacy-aware companies have become their own registrar because they decided it was just too scary to hook all their security to a company that has less security skills than they do themselves. So in the Netherlands, every bank is their own registrar, because that made them able to have a direct connection to the .nl people and not have someone else sitting in between.
Just going back to the DNS hijacking, you said that it's not very common, but I just wanted to understand when it's flooded with packets, because you previously explained that DNS is UDP and they're not ordered, they can just sit and it will just confuse it at some point and think, oh, that must be my reply. That's what you mean?
Yeah.
Okay.
Yeah, that's the trick. And it used to be very easy to do that. You had to figure out only this ID field, this 16-bit ID field. And that was trivial to do. That was really simple. People could do it in 2 seconds.
Is it something you should be worried about today?
No, because an RFC was written. Actually, I wrote it. That said, well, actually, we don't need just a random ID field. We also need a random source port. And with a fully random source port, you just suddenly went from 16-bit security to 32-bit security, which is still not luxurious, but it turns out that if you try to spoof 4 billion packets, the people do tend to notice.
Okay. Can I move us on to amplification attacks?
Yeah, oh yeah, sure. Oh boy, yeah, amplification attacks.
With so many IoT devices, I guess it's still out there.
Yeah, it is still out there, and actually at times it becomes huge. So the whole idea there is that you take a device that does not have that much bandwidth, and you make it send 1,000 small DNS queries per second, which is maybe all you can get out of this small device. And then but the queries you send out are designed to create huge answers. So you send out these 1,000 small queries per second, and these small queries generate gigantic answers of maybe 2 kilobytes each. And then suddenly you created from your bandwidth limited device, you just created a 20 megabits per second attack, which of course still not a lot unless you have thousands of devices again. And from time to time, and the trick is then to send out a query from a fake IP address. And then what happens is your answer goes out from this fake IP address, and then the response goes to that real IP address. And if you've picked your address right, you can send out a limited number of questions from fake IP addresses and then flood the real IP address with great force. And from time to time, last year, late 2019, someone decided to attack the PowerDNS name servers this way, and we have no idea why. We have no idea why someone did it, but it's still big, and the practical upshot of this is that you should monitor your name servers. That's really the only. You can rate limit them. So modern DNS software is able to rate limit itself. That has its own challenges. But your high performance name server might be part of a high performance botnet without you knowing it.
That would be a public name server, wouldn't it?
Yes, these are public name servers, and we saw it as a bit of an interesting challenge to see how well do we deal with a few hundred megabits per second of attack.
So that would be your authoritative name server. that you've got.
Yes, those were our own corporate name servers, and so we took this attack as an opportunity to learn, and we did learn a lot, I have to admit. Yeah, you would have to rate limit yourself or be behind someone else's denial of service scrubber or something like that. But the DNS does attract some larger amounts of traffic than you would expect, maybe.
We've got a good article on the IEEE Computer Society website on securing DNS in the cloud era that goes into that. So I've got a link in the show notes for listeners to pick up on.
Yeah, I would recommend everyone to read that link because this is not a concern to you until it happens.
Yes, as is everything.
As is everything, but this is something that can go well for a decade. And then suddenly you're like, oh, turns out that I've protected everything in my network except this.
Okay, so can I move us on to poisoning attacks?
Yeah, you could. So the art of DNS poisoning is that whenever you ask a DNS question, it's not a simple question and answer protocol. So, for example, if you ask the question, what's the IP address of PowerDNS.com to the root servers, you don't get back an IP address. You get back the name of other name servers where you could ask this question, and there's another section that says, well, helpfully, here are the IP addresses of the other name servers where you could ask this question. So whenever you receive a DNS answer, you might find more stuff in there than what you actually asked for. And this more stuff means that a resolver has to take a very critical look at what it received in the answer to see which parts in there it should actually be believing or using. And back in the really old days, and you can still read this in the original RFC standard that is still in force today, RFC 1034, and it will tell you that an authoritative server may helpfully give you more answers than you asked for, and it recommends that you use those answers. And the problem there is that if I ask for PowerDNS.com, I might get an answer for different records that I never asked for. And originally people would actually use those different answers and store them in the cache. So I could just send you a new IP address for bigbank.co.uk, and resolvers would say, oh, thank you, that's very helpful, and we'll use that from now on.
Yeah, because you're caching it, you can deliver what else you want.
Yes.
And
yes. So it's the full name is actually cache poisoning attacks, where you try to put stuff in the cache that is false, and that used to be possible by attaching additional answers to questions that would then be accepted, because the standard said as much. It said, yeah, you should accept that, and only in later standards did this advice was revoked and said no, don't ever. So I think that the original enforced DNS RFC is 1034, and that was fixed only in 2182. So we have advanced a lot of RFCs before someone said, well, maybe don't let everyone poison your cache. These days it's solved. It's an almost solved problem, by the way, except that there are still techniques by which over days, if you have days of time, you will still be able to perform cache poisoning, but you need days of hundreds of megabits per second of DNS answers.
So the DNS hijacking and cache poisoning, should that be discounted from my list, or is it just something to keep an eye on?
It is not the biggest worry right now. It's if you care about this stuff, and I think you should care about this stuff, of course, is let's say you have a name server and you see that it's receiving a gigabit per second of traffic all day long. That someone would within a few days will be able to poison your name server, and that's the state of the art. And that's something to watch out for. But so in theory it's a risk. In practice, we don't see a lot of it. But that's. I mean, the year is still fresh. You don't know.
Is this something developers need to worry about, or is it their upstream?
No, it's not something you. I'm trying to figure out what the developer angle for that is. But one thing you might want to look out for is that if you have a user behavior, if you have untrusted users, that could make your system perform DNS lookups. That would allow them to open a window for this kind of cache poisoning. So it is not harmless if untrusted users can force you to do DNS lookups. And that's something maybe to look out for.
Yeah, so I imagine something user-facing where you've got a maybe type ahead search and you're not sanitizing that properly and just querying domains to check something.
Yeah, that kind of stuff, yeah.
Or you're doing reverse DNS lookups in your server-side application type thing.
Yeah, or if someone has a form and they can enter a URL in there and you try to check the contents of that URL. Those are things that could make an untrusted user make your server do DNS lookups.
Yeah, that might be the nice features on creating a thumbnail image on some type of profile or something where your system is trying to go and look up that URL to get some content.
Yeah, exactly. And we actually, one fun thing that we do from time to time is if you post a URL on Twitter, then name servers all over the world will immediately start trying to resolve that domain name. And that's like hundreds of name servers immediately do that, no matter what you post on Twitter.
So you could use that as a amplification type thing.
Yeah, I actually think there is it does teach you something about the world and who is monitoring these domains and what name servers they are using and where they are from. There is an information leak going on there, and in general, DNS will leak your secrets because computers do so many of these queries based on what they see. We found a very interesting bug. I think it was in Sublime Editor, but I could be wrong. Where if you highlighted a piece of text, then the editor would sometimes think it looked a bit like a URL and would take your highlighted text and perform a DNS lookup with that highlighted text in there. That was a very scary information leak because people do copy-paste passwords a lot.
Yeah, exactly.
Yeah, and it was fixed very quickly, but it was the kind of thing where we thought, DNS is a window on the world, and it will just send out stuff random. I mean, if you look at the log file, most name servers do not log because it's so much. But if you look at the log file of a name server, you see the craziest queries come in from people that copy-pasted half a sentence, and that sentence ended on PowerDNS.com. And then you get that whole sentence as a DNS query. It is a zoo.
Yeah, I think there's some online tools to look at that sort of things that have leaked out.
Yeah.
Calling all developers. There's no telling what you can create when you upgrade your data platform to InterSystems Iris. Are you ready to build the applications you want, however you want them? Are you ready to develop applications faster than ever? Collaborate, build faster, and deploy more efficiently. Tomorrow's next breakthroughs are waiting for you today. InterSystems Iris Data Platform. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris.
Okay, so far we've spoken about the attacks. We've covered the overview of DNS, and at the moment it's quite naked. We've just got to trust it. All sorts of things can leak out. So where does that lead us to? How can we think about our privacy, our integrity, the big E, encryption?
Yeah.
Is DNS completely flawed at the moment, or where are we?
Yeah, so we do have DNSSEC, for example. DNSSEC adds integrity to DNS, so it means that if you have an answer, you can validate that you got the right answer.
And do you mean I, as a software engineer, should validate that, or is that done before me?
Yeah, that's the interesting bit. That's the really interesting bit. The software people, we have not been able to get the software people to do this. So what do I mean by that? Code applications that use DNS have decided that they are not going to validate DNS answers. So even browsers, which are like very good with security, they will simply ask a question of a name server and they will trust the answer. Technically speaking, it's entirely possible for a browser to validate DNS answers using DNSSEC, and a surprising number of domain names are now DNSSEC signed. Browsers have just decided, we're not going to do it because we put our trust in TLS certificates. We think those are better.
And what is that actually signing?
So it signs, and it is sort of interesting. What it signs is basically a piece of knowledge. So if you compare TLS, for example, or SSL, that is what we call transport security. So it will sign whatever for you, and you know that the data you received is the data you should have been receiving. DNSSEC works way differently, and it works a lot closer to how PGP or SMIME work, in the sense that DNSSEC actually signs the final answer to your question. So you get an IP address for PowerDNS.com, and then there's a DNSSEC signature below it, and that actually signs that IP address. It does not sign the transmission of the IP address, it signs the actual name IP address combination. And that has made it difficult to implement, but now that we have it, it is there. And collectively, all application developers have said, yeah, whatever, we're not going to do it. We're just going to use whatever our programming environment does when we tell it to look up an IP address.
So like the DNS library that
Yes.
the operating system's using, or
Yeah.
you could choose to do it yourself, can you?
Yeah, there are very fine libraries that allow you to do it yourself, and then you could verify the DNSSEC signature, and it will be more secure. And collectively, everyone has said, yeah, we're not doing it. It is really sad. I do understand it somewhere, because we have just put our collective trust in TLS certificates being correct.
But it's the same as, you just having a web form, and you don't sanitize the inputs, and you don't do cross-site request forgery checks, and it should be that sort of level with DNS if it's a critical application.
Yeah, I do think there's a little bit of difference there. We can honestly say that as long as we trust TLS certificates, then the IP address does not matter. We can just say, look, whatever we can use 1.2.3.4 for all our communications, and just rely completely on the TLS certificate checking to be correct.
And what is the IP address?
Yeah, basically it doesn't. The idea behind that is that you put all your trust in the certificate verification of HTTPS, basically. And if you trust HTTPS to message integrity or your transport integrity, you no longer care about the IP address, because the IP address is at that point is just no longer mattering for your security, because the transport has been has integrity.
So you don't need to worry about DNSSEC if you're encrypting.
Yeah, you could take that. You could take that view, and actually, not only could you take that view, that is the view that everyone has taken. Where they say the IP address doesn't matter because we just assume it's fake already. We get our security from verifying the TLS transport, and it's fine up to a point until you've seen that there have been hijacks where people hijacked the DNS name briefly, and then were able to get themselves a whole bunch of new TLS certificates based on that brief hijack. And that is the kind of place where DNSSEC validation would have helped. And the Let's Encrypt people are now also doing that. So that's nice. So there is a role for DNSSEC, but right now people are just not doing it.
Yeah, there's a chicken and egg scenario there, where a lot of companies, to validate you own the domain, ask you to do what you discussed in the introduction by hosting a text record on your website or your domain name record. So if you've hijacked the record, you can then get the certificate to prove that if you're running DNS over HTTPS, it's yours. We actually did a show, episode 378, with Joshua Davies on attacking and securing private key infrastructures, PKI. So if listeners can jump on there to see what you can do to actually get that DNSSEC broken. So if you want integrity without encryption, you've got DNSSEC. But if you move DNS queries over to TLS or HTTPS, you can kind of drop DNSSEC with the caveat that you've just explained. So what does that bring us?
Yeah, where does it bring us? I think that the internet security is still, right now, still a web of cards, or a house of cards. As long as you are able to take over control of a domain name, you can do a lot of terrible things to people's certificates. And there are ways to pin certificates, but they're not super strong. And I think the world would have been a lot better if we had DNSSEC to, well, at least tighten up control of that text record phenomenon that you mentioned, that if you're able to manipulate a single text record on a domain name, that you're able to do everything on it from that point on.
So at the moment, we've got the privacy concerns as well that are wrapped up in all of this. Do you want to take me through what privacy concerns there are without DNSSEC or encryption on the local network, enterprise network, or public Wi-Fi? Just briefly, and then we can drill into how we're addressing that and if that's the right way.
Yeah, so very briefly, you should realize that DNS traffic really tells you everything about a person. So if you only have access to someone's DNS records, you will be able to tell where they live, what phone they have, what brand of TV they have, which streaming video services they use, where they live, where they work, what schools they go to, what sports teams they like. DNS is per bit perhaps the most privacy sensitive material on the internet right now, because it tells you which hospitals you visit and everything. So it is very much worth it to protect your DNS records, because we don't want too many people to have access to those.
And is that because it has the domain name that you're querying to map through to an IP address?
Yes, exactly. So if you only have the DNS traffic of someone, you will see whatever they typed into their browser, or whatever app they launched, or if you have a webcam or a printer. I mean, if I look at the DNS traffic in my house, I can tell you exactly what printer I have and what phones people have, and when they play.
And how is that? Is there some other type of metadata in that query apart from just the domain name?
No, that's it. No, it's just a domain name. It's just a domain name. But if you look at what modern tools, what kind of DNS lookups they do, the whole name of my printer gets sent out as a DNS query, and the Nintendo Switch in our house wakes up at night and does DNS queries to see if there are updates or not.
So that might be to like Nintendo.com.
Yeah, or it goes to Nintendo Switch update server.com.
I see. Yeah, I'm just trying to understand how you map.
Yeah.
The query to the device.
Yeah, no, it's very descriptive of what's going on in your house, and it is. We did a small experiment, PowerDNS, with a data set that we have, which is pre GDPR. So it's a long time ago, but we tried to figure out if we could find ourselves in this huge data set, and based on only a few things like where someone lived and where they worked. So you basically look at everyone that makes a connection to imap.powerdns.com. and something with the name of the town in which they lived. And we immediately found our guy in this huge data set. Because he was the only one visiting powerdns.com and visiting the name of that village. So it is a very descriptive and privacy sensitive thing, and it's very much worth protecting.
And is that, for example, if you have all that information, how do you map that back to a person? Is it not just arbitrary data at that point?
Yeah, so this gets you to the point of what is pseudonymity, and if you have a list of IP addresses and domain names they visit, this very quickly becomes de-anonymized. So if I look at myself, I radiate a pattern where I visit lots of PowerDNS.com related content. I have a few other projects, and if you would say, give me all the IP addresses that visit the following 5 websites, that would always be me.
Yeah, so if there's an FBI request for Bert, for example, he's the chief architect of PowerDNS, look for anything with PowerDNS in it. You could go that way. But the other way around, how you would need something to look for, really.
Yeah, you would need to know something about it, but it's not that difficult. If someone has a Tesla, and I know that they work at a certain company, and I know the name of the sports team that they like, that every step in that narrows it down tremendously, and all these things radiate out of your internet connection.
And so, with this big list of leaking information, do these concerns go away if we switch to using DNS over HTTPS or TLS?
Well, the problems certainly move, because encryption, of course, cannot make the data go away, because this is internet. You have to, if you make a connection to to a website, somehow someone will know that you made a connection to that website. It's almost impossible to hide that. You can only choose which people do get access to that data.
Yeah, and if you were to profile your office connection, your home connection, there'll still be X amount of traffic coming from that connection between 8 and 6 p.m., for example, so they know you're there.
Yeah. Oh, that's the other one. That's the traffic data. So that's just the fact that you are using DNS queries.
Mm-hmm.
But the whole discussion that's going on now is where people say, look, DNS is unencrypted, and that's bad. And I am in full agreement with that. We should encrypt DNS every place we can. But the solution that people have chosen for that is say, well, right now, most of your DNS traffic is unencrypted between you and your service provider. So that might be Sky, or that might be BT, or it might be PlusNet. So they can see what you are visiting. And the proposed solution is then to encrypt DNS, which is good, and then send it to a new third party, and they then get access to all your browsing data. And that is a part where I say I'm not that convinced that actually is progress, because before we had this highly regulated telecommunications company, at least here in Europe, and so the telecommunications company knows what sites you are visiting, which is okay. Yeah, I'm not happy about that, but it's not progress if we then say, well, from now on this American company will know exactly what sites you are visiting.
Yeah, your telco's pretty much heavy regulated by the government.
Yeah, and that has upsides and downsides. That means that
the third-party DNS.
Yeah, the telco typically here is very regulated and has to adhere to GDPR or very GDPR-like legislation. And that means they are in a bad place to monetize your data. It doesn't mean it's impossible, but there are a lot of hurdles in place, and it's going to be very tricky to just start selling people's traffic data. And if the proposal is then, well, we want to encrypt your DNS, but in order to encrypt your DNS, we're going to send it to, I don't know, Google or Cloudflare. These are far less regulated places. Well, and these are the current proposals. The original story was that, we have to give it to Cloudflare because the big internet service providers of the world, they are not working on encrypting their DNS. And the good news is that has changed with many of the very largest internet service providers are now either offering or working on offering fully encrypted DNS. And with that, I don't see a lot of benefit anymore of sending all my encrypted data to a third party that I did not select.
So if we just take a step back, we've been able to do DNS over TLS, which is, I presume, the natural step. Throw a protocol over TLS and we're encrypted and we're done. Why are we not all on that in the world?
Actually, so this has been standardized. So there was an RFC, a standard that says this is how you do DNS over TLS. And then no one did it. Nothing happened. And why did nothing happen? For one thing, as we discussed earlier, people don't really see DNS as a security thing because they say, well, we're not trusting DNS anyhow, so we don't really care. And that was one reason, just the lack of care. The other reason is that DNS over TLS runs over port 853. So that's the normal DNS port, but then 800 higher. And port 853 is just simply blocked in most environments. You will not be able to send out a query on port 853 from most corporate networks because everything is now everything is blocked these days except port 443. So HTTPS is the new TCP. And so DNS over TLS didn't take off, one, because people really didn't care, and secondly, because most firewalls just blocked it.
So why HTTPS and a new protocol? I think you touched previously that port 853 is just not going to be opened in the real world, and everything speaks 443. So what does that protocol look like?
Yeah, so what they did when people got sort of re-energized on this and they said, we need to do encrypted DNS, they said, we're going to make sure that no one can block this. It was a design goal. It's stated in the first paragraph of the standard that says we want to do DNS that cannot be blocked. And the best way of not being able to block something is to move it to generic HTTPS queries and say, hey, everyone has to allow port 443 anyhow, so we're going to use that. So that was one reason why they moved to DNS over HTTPS. And the other reason was that browser vendors, who are of course the big guns in this game, they are very good at HTTPS. For them, HTTPS is sort of the basic unit of functionality that they work with. So for them, it was the most natural thing in the world to say, hey, we're going to use port 443 and HTTPS for everything, because that's what we do. And originally even, going back to your question, what does it look like? Originally even, their idea was to take DNS and just sort of do away with it and reformat the DNS query as JSON. And we all love JSON. It's because you can put everything in there. And they thought it would be good to sort of stop doing this ridiculous DNS protocol and move to JSON. And this got a pretty long way even before it was realized that porting the whole DNS semantics to JSON would actually be a lot of work. So then the decision was made to turn DNS over HTTPS literally into that. So you take a DNS query as formatted normally, so as it would have been in 1983, and then take that normal DNS query and put it in an HTTPS connection. And that's what it looks like. In that sense, it is not special.
So it'd be just like posting a file content.
Yeah, it is actually. It can be a post of content. It can also be a GET request. Both have their advantages and disadvantages. And it looks just like normal HTTPS traffic, except that the queries are very small, of course, and there are a lot of them. So it does look somewhat atypical from a network connection, because normally you would get small query and then maybe a megabyte of answer or whatever. And here you get small query and then also a small answer coming back, and then a lot of those.
And does this mean that we don't need to worry about any of the attack vectors that we spoke about earlier? Or does it bring a different set?
Actually, it does nothing really. It helps you against the attack factor that someone sitting on your network would be able to tell what sites you are visiting. It also does protect you against someone sitting right next to you on your network and trying to send you fake DNS answers. So let's say the attacker is in your house or in your own network. It would protect you against your own network.
Like some type of malware bot or something like that.
Yeah, or an evil, let's say a fake Wi-Fi access point or something like that.
And with these small packets, how fast is it versus UDP?
Yeah, that's a very good. So so it has been found that with sufficient statistics, you can argue that it's not that DNS over HTTPS is not much slower, but you do need quite some statistics to make that happen. I would prefer to look at it another way. A well-performing traditional DNS over UDP nameserver will always be faster than DNS over HTTPS, and by some margin even. If you, however, make the comparison between a not very well maintained resolver and a very well maintained DNS over HTTPS resolver, then you find that the very well maintained DNS over HTTPS resolver can in fact be as fast or even a little bit faster in some cases than the not very well maintained classic DNS resolver. But there is a significant overhead. And
from the point of view of an ISP or a network operator, can they prioritize this traffic over another type of HTTPS traffic?
Yeah, no. Actually, that would be extremely difficult.
Because they can't look inside it.
No, it looks just like normal traffic, and in fact, the delay is not so much due to congestion or other things, but simply because it uses so many more packets to get the same thing done. So a typical DNS query response is typically 2 packets, classic DNS. With HTTPS, we've seen this take 6 packets or more. So that's like a factor of 3 more. So there is always going to be, you cannot prioritize yourself out of a latency situation.
And I guess you've already got it implemented in PowerDNS?
Yeah, we were actually, so we were sort of really early with that. And there's a slight paradox in there that we've been arguing heavily against sending DNS to third parties, mostly in the US, because originally the idea was just that we would start sending all our DNS to Google and Cloudflare. And we thought that was a terrible idea for the autonomy of our networks and our privacy. But many people then started fighting DNS over HTTPS, and we thought that was misguided. We said, no, it's not the protocol that's doing anything wrong, it's what people do with it. So we then shifted to making sure that anyone could start doing encrypted DNS, so that all the large service providers of this world would be able to offer their own encrypted DNS, because encrypted DNS is good. So that's why we came out early with these capabilities, and have now also been able to scale them up for use in really large-scale networks with tens of millions of people on there. So while we decry the move of DNS to less regulated third parties, we were very enthusiastic about making sure that the protocol was easily implemented.
Well, you've pretty much squashed my last few questions in that section with that answer. That's really good.
That's efficient.
So if it's so perfect, what problems are there still to work out?
Yeah, one of the issues with, one of the fun things, let me put it the other way around, about classic DNS, is that because every query is just a single packet, that means that browsers could just send out 25 queries and wait for answers to come in. And some answers might come in earlier, some might come later. So for example, if you send 2 questions for the IPv4 and IPv6 address, the IPv6 answer might come in earlier, sometimes the IPv4 answer might come in earlier, and the browser can just simply use the first answer that comes in. If you send your queries over DNS over HTTPS, that is actually a connection-based protocol. And being a connection-based protocol means that if the first question has not arrived correctly over at the resolver, the second question will also not have arrived correctly. The second question can only be processed once the first question has arrived, and this is called head-of-line blocking. And this is a well-acknowledged issue in DNS over HTTPS, and for this reason there are now valiant attempts ongoing to move HTTPS, paradoxically again, from TCP to a UDP-based protocol called QUIC, QUIC. This QUIC protocol then brings the sort of out-of-order benefits of UDP to HTTPS. And that is a big ongoing effort right now, but it's turning out to be hard work.
This isn't part of the HTTP2 spec.
No, this is actually part of the HTTP3 spec.
Okay.
Because it turned out that HTTP2, for all its glories, did ship with the head-of-line blocking issue that you just get when you use TCP. So in that way, DNS over HTTPS is actually currently a step backwards in terms of sending out parallel queries and operating on less than perfect networks, because this is all about packet loss, by the way. I had to clarify, a single dropped packet will now cause DNS over HTTPS to come to a standstill.
Given all the intelligent people dealing with this, you as a given also, how did RFC 8484 get out?
Yeah, I think the best answer to that is that many of the people involved live in the US. And in the US, the privacy situation from service providers is just dire. They will sell all your data all the time. And from that perspective, they argued we need to do something that cannot be blocked by Verizon. And the only thing that they could come up with that could not be blocked by Verizon was DNS over HTTPS. And given the background that we have to do something, and this is something, then you could end up with the DNS over HTTPS RFC. And then you can, of course, have the privacy worries where you say, well, look, if we now start sending our DNS to another third party, maybe they will also sell all our data. And then they said, no, we're going to sign really good contracts with those people where they promise not to sell our data. And then they arrived at the sort of nirvana for them, where they said, well, we've solved the Verizon selling all our data problem, and we have a contract that says that this new third party will not sell all our data, and presto, we're done. We achieved something great. And from the US perspective, I can understand where they are coming from.
What benefits do you see that have come out of this apart from DNS being encrypted?
Well, that is, of course, just a major benefit, DNS being encrypted. We should not overlook that one. If anything else has come out of it, it has been the importance of DNS and indeed the raising of awareness of how little we are actually doing in protecting it and looking at it. So it is suddenly on everyone's radar. And DNS has always been sort of underappreciated, under-maintained, sitting quite uncomfortably between networking and application departments. In many organizations, DNS doesn't live anywhere. There's no team that says we own DNS. It's sort of, it's not quite the network, it's not quite the application. In many service providers, it also doesn't live anywhere. And this has really put DNS on the map. So I would say that may be beyond the very important part of encrypting DNS. The biggest benefit may have been putting DNS on people's radar.
Okay, thank you. I'd like to wrap up the show now. Obviously, DNS is extremely important for us all. But if there is one thing that a software engineer should remember from our show, what do you recommend that to be? It's a tough one. I always ask this type of question at the end.
No. It's a very good thing that you asked this. Monitor it. That's really. I realize that this is not quite the software, from the software developer standpoint, but when DNS breaks, everything will break. So it is worth adding a little bit more diagnostics to it and maybe being a little bit more aware of what happens. And as one concrete example that you could think about, DNS, if you have long-lived applications, the actual DNS answer that you got at the startup of the application that you cached from weeks ago may no longer be the actual right IP address. DNS is more dynamic than it used to be, and we still see many applications that do a DNS lookup at the very beginning of what they do, and for example to find the IP address of the database, and then it will stick with that address for the next 5 years.
Yeah, we see that in the telco world where you're using voice over IP and you've done a lookup at the start of switching on the phone system.
Yeah.
And then obviously you're using DNS for some of its other features to do with load balancing and things. And that IP address has changed because it's down. So that fits exactly what you just said.
Okay, well that would be my one thing.
Okay, and normally when we're doing connection-based programming, it's a great practice to have some type of timeout to make sure it's just not sitting there forever. Is there something similar you can do with DNS to check? Would that be to look for DNSSEC, or just if you don't get an answer within a certain time, move on, or is that handled by the libraries you use?
Yeah, it's a good question. It's typically handled by the libraries that you use, and very often you also have no control over it. So it's quite
not
typical.
Something I see exposed.
No, and it should be, because you cannot just a native DNS lookup might take as much as 10 seconds, and you would only hear about it failing maybe after 10 seconds, and that can be a big downer for any kind of performance or failover to a secondary thing. But still, there is no solution for it, because a bona fide DNS query can actually just take 6 seconds to complete. There are important domain names. A famous one was in nature.com, the famous science journal. And they had such a convoluted DNS setup that if your name server was not already aware about nature.com, it could easily take like 12 seconds to resolve the nature.com IP address. And subsequent lookups would be very fast, because it would have all the related data in the cache already. But there is no guarantee that you will get a DNS answer within any reasonable amount of time, which is actually one reason why in some of our stuff we personally do not use DNS, because we were like, I don't know when I'm going to get an answer.
Yeah, maybe that's the take home from today, is to be conscious that DNS can take a while, and it's something you should maybe bring into your application.
Yeah, and the other thing that people could maybe think about is DNS records have a time to live. And this time to live is just that says you can cache this answer for 1 minute or 5 minutes or 1 hour or whatever. And these numbers are typically set extremely low. So even though there is no chance of this IP address changing 60 times per hour, we still set the TTL record to 60 seconds because maybe one day we need it. And it turns out that if you take this IP address and you give it a TTL of half an hour or even an hour, then everyone using your stuff just gets better performance. And the downside is that maybe one day you need to change the IP address and it will now take an hour before everyone notices. But I have news for you. Even if you put the TTL on 1 minute and you change it after 1 minute, not everyone is using the new IP address. So if there's one thing to look out for, it's ridiculously and needlessly low time to lives on DNS answers. And if you upgrade that to an hour or half an hour, then everything will just suddenly become snappier for everyone.
Oh, interesting. Thank you. Is there anything I missed that you'd like to mention?
No, I think this was well-rounded, and we did not get bogged down too much in well-visited areas of the DNS over HTTPS discussion.
Yeah, I've linked into the show your YouTube talk that you did at NL Nog last year.
Yeah, that
I've also linked in Paul Vixie's one.
Also good.
EuroBSD, which was really good. So where can people find out more? You've got 2 Twitter's accounts, I think.
Yeah, I think the DNS one is at PowerDNS_Bert. And that's why I publish most of my DNS related things.
Yeah, that's where I follow you and see most of your tweets.
Yeah, no, that's probably the best one for if you're interested in DNS.
Excellent. Well, Bert, thank you very much for coming on the show. It's been a real pleasure. This is Gavin Henry for Software Engineering Radio.
Okay, thank you very much.
Thank you for listening.
Developers, take your marks. It's time to upgrade your data platform to InterSystems Iris. It's time to deliver complex mission-critical applications in the fastest route possible. It's time to use any data from any source. It's time to embed analytics and create interactive user interfaces. So what are you waiting for? Choose your language. Choose your tools. Choose your environment. Collaborate, build faster, and deploy more efficiently. Done and done. Tomorrow's next breakthroughs are waiting for you today. InterSystems Iris Data Platform, the fastest way to build applications. Ready, set, code. Start coding for free. Visit intersystems.com/try to try Iris. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.